So this is the second topic in our little mini unit. Still kind of going off the story problem idea. This is back from chapter 3, something called related rates. And so while we were back in chapter 3, if we had done this chapter in order, we would have just finished the implicit differentiation section. That was 310. And so right after that, we just started talking about, we did the chain rule and then we did implicit differentiation. And what we do with implicit differentiation is anytime that you have a different variable, so say you come across a y, but you're differentiating with respect to x, you always toss in that dy by dx. Kind of like a chain rule sort of application. And so that's exactly what we're doing with related rates, except related rates are all different quantities that are related through time. It's all of these things that are changing with respect to time. So first example we're going to look at is water being drained out of a conical tank, a cone-shaped tank. The volume, the radius, and the height are all related to time. They all change as time changes. So you might say something like, water drains out at a rate of 1 gallon per minute or something like that. And so then the radius would be changing per minute. The height would be changing per minute. That's every single problem that we're going to look at in this section. All right, so here's how this works. We've got an equation. We figure out how the variables are related, and they're related by the volume of a cone, which we've got written right there. V equals 1/3 pi r squared h. You differentiate implicitly with respect to time, and then you get something called the related rates equation. Okay, so we've got this formula right here. We're going to take the derivative with respect to time of both sides, so of the left and of the right. Oops, forgot the 1/3. Okay, so we take the derivative of both sides with respect to t. So this on the left-hand side, it's just a v. So the derivative of v with respect to t, we literally just write dv by dt. So that represents how the volume changes as time changes, the rate of change of volume with respect to time equals, and then this thing, we've got a 1/3 pi, that's a constant, we can leave that out front, and then the r squared h, we're going to have to do a product rule. So we start with the first, which is r squared, times the derivative of the second. So derivative of h with respect to time, we write dh by dt, and again that notation literally means the derivative of the height with respect to time, plus the second, which is h, and then times the derivative of r squared with respect to time. So the derivative of r squared is 2r, and then dr by dt. Okay, so you'll always have these quantities like this dv by dt, dh by dt, dr by dt. You're taking the derivative of every single quantity with respect to time. All right, so then the sentence here, you can see that the volume changes as the radius changes, as the height changes, and it's all changing as time changes. All right, so first example, we've got a pebble being dropped into a calm pond. So what I'm going to do is I've got this example and then the guidelines. We're going to go back and forth in between this example and the guidelines. Okay, so pebble is dropped into a calm pond, causing ripples in the forms of concentric circles. So you read that sentence, and I am hoping that the first thing that pops into your mind is to draw a picture. So pebble's dropped, and then you've got, circle, another circle. That's what it means to have concentric circles. And so this thing is just continuing to grow. You've got, when we talk next, the radius r. So we can measure the radius, and that's from where the pebble was dropped out into the outside of the current circle. It's increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so back down to the steps. So step 1, identify given info and needed info. Given info and needed info. It's another way of saying like the known and unknown information. I like to say given and needed because given sounds pretty obvious. It's what they give you in the context of the problem, and then what you need to solve the problem. So we're always going to set up with these problems kind of a little like sidebar where we write down what's given and what we need. All right, so the given information, let's write down we have. The given information comes in that second sentence. The radius r is increasing at a constant rate of 1 foot per second. So this is a rate of change. It's the rate of change of the radius with respect to time. So what we write in our notation is dr by dt. So again, when it says it's increasing at a constant rate, it's the rate of change of the radius with respect to time, and that is 1 foot per second. Okay, so that's given information. That's the only rate that's given to us. We're given one value right here, but it's not like the radius is always 4 feet. So really that's kind of part of what we need, and I'll write that down just right now. Okay, so what we need says at what rate is the total area changing. So what we need is dA by dt. But not just any old time, we want it when the radius is 4 feet. Okay, so we want how the area is changing at the point when the radius is 4 feet. So that's our given info and our needed info. Make and label a sketch is also part of the first step. Okay, so we kind of already did that. We've got this little sketch. We know what the radius looks like, and then of course we know the area. Step 2, write an equation relating the variables. Write an equation relating the variables. All right, so what we do with this is we look back, so we're like, all right, we're talking about the radius, we're talking about the area, it's a circle, so what equation would relate to all together? Well, that'd be the area of a circle, because of course you've got the area covered, and then the radius is one of the variables in that formula. So the equation is just the area of a circle. That is the equation that kind of pulls all this information together. So this is the little sidebar that we're going to have set up for every single problem. Our given info, our needed info, and the equation that ties those things together. Okay? On to step 3. Step 3, implicitly differentiate both sides with respect to time. So this is very important. In all of these problems, all of the implicit differentiation problems, we're implicitly differentiating with respect to time. Because that's how all of this stuff is changing. You know, 1 foot per second. The area formula is going to have a similar unit. All right, so we start with this equation. It's actually just what we did up here when we took this derivative with respect to time. So we're going to take the derivative of the area function with respect to time. So d by dt, get used to writing that. It's always the derivative with respect to time. Okay, so we take the derivative of the left, the derivative of the area with respect to time. We literally write just that, derivative of the area with respect to time, equals, and then we take the derivative of this. Remember, pi is just a constant. So the 2 comes out front, multiplies by the pi. R's power drops down to 1. But then we do kind of a chain rule sort of thing. Because r is a different variable, we have to throw in that dr by dt. It's like the derivative of the nested function. Okay, so that was the third step. We did our implicit differentiation. And the fourth and final step, after differentiating. It is very, very important that you do this step last. So after, and only after differentiating, sub in the info and solve. So while we're looking at that formula, I always want you to keep an eye out for what we're solving for. So we want at what rate is the total area. So what we need is dA by dt. So always kind of keep that in mind. Know what we're trying to solve for. We're trying to get that thing by itself, and so we're going to plug in everything else that we know. So dA by dt equals, we've got 2 pi. We want it at the instant when the radius is 4. So that's when we plug in the 4 right here. And then dr by dt is 1. And so we sub that in. So we simplify this up. 2 pi times 4 times 1 gives us 8. So 8 pi. And then always think of the units too. 4 is 4 feet. And then 1 was in feet per second. So this ends up being feet squared per second. Okay, so that's your final answer. At the instant when the radius is 4 feet, the area is increasing at a rate of 8 pi feet squared every second. So in the second when it went from 4 feet to 5 feet, the area would increase by about 8 pi feet squared. All right, let's look at the next one. let's practice a couple of these. Translating some rates of change. So the velocity of a car after traveling for 1 hour is 50 miles per hour. So velocity is actually the rate of change of position. So we always use S for position. And it's after the car has been traveling for 1 hour. So that's at t equals 1 hour is 50 miles per hour. Okay, so that's what that means. It's the rate of change of the position with respect to time. That's what velocity is. And then you do that little Leibniz notation at t equals 1 because they give us that specific information. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. So when water is being pumped into something, you can always look at the unit, first of all, if you're unsure. This is a volume change. This is the rate of change of volume. And it doesn't give us at a specific time when this one is, so you can kind of assume it's like a constant rate of change. It's 10 cubic meters per hour. Okay, last one of these. A gear is revolving at a rate of 25 revolutions per minute. Each revolution is 2 pi radians, so 25 revolutions would be 50 pi radians. So whenever we talk about revolutions, any sort of angle or radian thing, we always use theta. So the angle with respect to time is revolving at 50 pi radians per minute. Okay, so just kind of practicing that whole story problem idea of seeing words, seeing phrases, and translating them into math. All right, example 2. Very, very similar. We can kind of follow our step by step. So air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. We've got our given information right here. We can figure out in the next sentence what we need. So let's start. Our little sidebar is always going to be given, need, and equation. So what we are given, air is being pumped into a spherical balloon. Again, if you're unsure of what the quantity is, just look at the units. Cubic feet is always volume. So this is the rate of change of the volume with respect to time. And it's being pumped in, so we know the volume is increasing. So it's a positive 4.5 cubic feet per minute. That's our given info. We'll use that in the last step. What we need is written in the second sentence. Find the rate of change of the radius. So that's dr by dt when the radius is 2 feet. Okay, last thing is the equation, or last thing of this first step anyways, is the equation that relates them together. So it's being pumped into a spherical balloon. So when we talk about the volume of that balloon, we're talking about the volume of a sphere. So this is something that, whether you know it off the top of your head or not, hopefully it sounds familiar. This is 4/3 pi r cubed. That is the volume of a sphere. Okay, so that is our sidebar. That's all of our necessary info. We've got what we are given, what we need, and the equation that relates those variables together. Next step is to implicitly differentiate both sides with respect to t. So we take this equation right here, implicitly differentiate both sides, always with respect to t. Okay, so derivative of volume with respect to time, we write dv by dt, equals, over here our only variable is r. Remember, pi is a constant. 3 comes out front, multiplies by 4/3, I get 4. Pi stays right there. Power on r drops down to 2, and then kind of like a chain rule thing, I multiply by the derivative of r with respect to t. Okay, so that's my equation so far. Take a look at what I need. What I need is this value right here. So that is what I'm going to end up solving for. So all of the information that I have so far, I can plug that in. That should be the only thing that's left. So dv by dt is 4.5 equals 4 times pi. And then when the radius is 2 feet, that means I'm plugging in a 2 right here. And I need to solve for dr by dt. All right, so I start simplifying up. So 4 times pi times, this is another 4. This is 16 pi, so I can divide both sides by 16 pi. Okay, so if we want an exact answer, which maybe we do, maybe we don't, I would never leave a decimal inside a fraction, but what you can do is multiply by 2 over 2. So 4.5 times 2, of course, is 9. 16 pi times 2 is 32 pi. So that's an exact answer, but you might be looking at that and have no idea what that means, because you probably wouldn't be able to estimate too well what 9 divided by 32 pi is. So it is approximately 0.0895, and our units would be feet per minute, because we're talking just about the radius, which is a one-dimensional unit. So any of these values right here. Okay, so one thing to point out, since we just finished talking about this problem, at the beginning of the problem, we were told that air is being pumped in at a rate of 4.5 cubic feet per minute. That is a constant rate. So dV by dt is constant, it is unchanging. But now notice that dr by dt is all dependent on these values right here. It's dependent upon the radius. And so even though dV by dt is constant, dr by dt is not. And that's actually totally normal. So you could set one of them constant and then the other variable would change as time changes. So note, the volume has a constant rate of change. Radius does not. And if you think about that, if every minute you're pumping in 4.5 feet cubed per minute, the larger the balloon is, the less that's going to affect the radius, because your volume is already so big at that point. All right, it's our conical tank problem. Conical tank has a height of 3 meters and a radius of 2 meters at the top. I see that sentence and I instantly want to draw a picture. Okay, so the height is 3 meters. So that is what we've got on the outside here. So 3 meters, top to bottom, and the radius is 2 meters at the top. Okay, so those are some measurements there. The water level is rising at a rate of 0.3 meters per minute. Okay, so that's what we're given. The water level. The water level is the height of the cone. So this is dH by dt. And it's rising, so we know it's going to stay positive. So 0.3 meters per minute when it is 2 meters. So this specifically is dH by dt when the height is 2 meters. So it's not a constant rate of change. It's just at one specific instance. At what rate is water flowing in? So what we need is the volume, dV by dt. Okay, and we want it at that specific instant when h is 2. Okay, so these cone ones are a little bit more complicated than some of the other ones, and you'll see why once we write down this equation. So since we're talking about volume of a cone, we use the formula that we had on the previous page, the volume of a cone formula, which is this. So that's our sidebar. That's all of our necessary information. Here's what makes this complicated. I'm given information about h, I'm given information about v, all of a sudden there's an r squared that pops in there somewhere. Okay, so here's what we do about it. If we look back at this picture, the water is going to be in here somewhere. Like the water level might be somewhere around there. And so this is the radius, is just that measurement. The height is just whatever goes up to where the water is. And so what you may not know, but what you need to remember for these problems is that a cone moving up and down like this, it's constantly got similar triangles. And so we set up this little similar triangles thing where if you look at the whole cone, this is 3, this is 2. If you look at like a slice of the cone, wherever the water level is, we're calling this R and this H, those are similar. And so what I'm going to do is I'm going to use that relationship to sub out the R in this equation. Okay? So I know that we write this, like 2 over 3 is equal to R over H. We set up those proportions, which means that the radius is always going to be 2/3 of the height, which should make sense. As you move up and down this cone, the radius at the top is 2/3 of the height. And so as you move up and down, the radius will always be 2/3 of the height. So I'm going to sub that into my equation. Okay, so let's clean this up. So 1/3, here's 2/3 squared, which is 4/9. 4/9, and then I have to multiply by 1/3. So that's 4/27 pi. This gives me an h squared, then times another copy of h. So that is my volume formula. I got it in terms of one variable, and I was able to do that because I know the relationship between r and h based on my original cone. Okay, so that's my equation. I kind of finalized it when I made that substitution. So my next step is to implicitly differentiate both sides. So when I take the derivative of v with respect to t, I get dv by dt equals. Then when I take the derivative of this right-hand side with respect to t, I've got my coefficient that was already there. And then times 3h squared, that's the derivative of the h cubed, But then with my chain rule, I multiply by dH by dt. Okay, so that is my function. I took the derivative with respect to time, t. So what I need is the rate of change of the volume. That's what I'm trying to solve for. So all I'm going to do is just plug everything into the right-hand side and simplify that down. So equals, I've got 3 times this, which gives me 4/9 pi. I plug in h. The value I was looking for was when h equals 2. And then I plug in dH by dt, which is 0.3. Okay, so these are some kind of ugly values. I would recommend just plugging this right into your calculator. You don't have to if you don't want to. Like you could do 2 squared is 4 times this gives you 16. The 0.3 and the 9 would reduce down. But this it would get ugly. It would get ugly pretty quickly. So I would probably just plug it into your calculator to get a decimal approximation. What you get is approximately 1.676. That would be meters cubed per minute. Because you know that the height is just meters per minute. So volume, of course, is always a cubic unit. Okay, let's do just these important formulas. Okay, so then when you're looking what you're doing in class, you'll have those. So important formulas. Spheres, area and volume. The area of a sphere is 4 pi r squared. It's like surface area. The volume of a sphere we had in a previous problem, 4/3 pi r cubed. Circles. The circumference of a circle is 2 pi r. The area of a circle is pi r squared. So these are all formulas that should be familiar. If you don't know them, like I'm hoping you know a lot of these, but if they better look familiar, I'm hoping, at least, from geometry. Cylinder. To the volume of a cylinder, pi r squared h. So you've got the circle, which is pi r squared, and then you go up the length of the height, and that gives you the volume of a cylinder. We could also have the surface area of a cylinder. So surface area of the cylinder adds the top surface to the bottom surface, and both of them are pi r squared. So we've got 2 pi r squared. And then picture like the outside of a circle really actually is a rectangle. The outside of a cylinder. Picture like slicing into a toilet paper roll and opening it up. It's really just a rectangle. And the rectangle has a length of 2 pi r, because that's their circumference, and then a height of h. Okay, so that's the surface area. One thing that I want to note on the volume. If you're in a cylinder, the radius is going to be constant. So picture like a cone. As you move up and down the cone, the value of the radius changes. But if you're on a cylinder, you move up and down that cylinder, the radius is not ever going to change. Okay, cones. Volume is 1/3 pi r squared h. It's exactly 1/3 of a cylinder. And what you want to keep in mind here, when you're trying to solve these, if you want to sub in for r or for h, you use similar triangles, just like we did on that previous problem. And then these 3 are going to come up tomorrow, but let's get these formulas out of the way right now. If we have right triangles, you use Pythagorean theorem. I'm hoping we know that formula. If you have similar triangles, you would say like A over B, that would be like the short side and the long side of one triangle, and then equals C over D, short side and the long side of the similar triangle, just like we did in that cone problem. And then if you have anything to do with angles, if they're asking you how an angle is growing or how an angle is shrinking, look at the sides that they gave you and then figure out whether sine, cosine, or tangent is most appropriate. All right, let's get these important tips down and that'll be it. Important tip number 1, make sure you separate the constant info from the variable info. So like on the previous problems, even though they said like we want the rate of change of the area when the radius is 4, doesn't mean the radius is always 4. It means the radius is 4 for an instant, and that's when we want to know the area. Whereas something like a cylinder, saying that the radius is 4, that's constant information because that's not changing. So be careful with that. Important tip number 2, make a sketch. Always, always make a sketch. I should never walk around and see you guys not sketching things out because it gives you such a visual of what you have and what you still need. And number 3, this one's very important. Remember, there will always be a way to find all of the unknowns. And that last tip will be more important in the stuff that we're doing in the next lesson tomorrow, like the rest of these notes, because there will be so many variables and it will seem like, well, I don't know this, I don't know this, I don't know this, but there will always be a way to find all of them, and we will experiment with that a little bit more in the next session.